Hey, so this is the gas chapter, and there's a lot of stuff to take in here. This will be a little more difficult than last time. What we have is a simulation that I really highly recommend you do to get the basics that are true about gas. As you can see, you can add more gas by pumping this pump. And when I did that, the volume got bigger because there was now more gas in there. Think about putting air into a balloon or to a tire, right? It gets bigger. Then there's a point where it can't get bigger, and adding more molecules is increasing the pressure. And that should make sense to you, right? The pressure ultimately boils down to basically how often these air atoms or molecules will bounce against a wall. So the higher the pressure, the more bouncing, the more the pressure is. So we can increase that pressure. You might consider by heating them up, that'll get them moving faster. And we could decrease that pressure by cooling them down because that'll get them moving slower. So now what you saw here, rather than decrease the pressure, the volume went down, which is also something, if we heated it up, the volume would go up, right? Because now there's more things moving around. Think of how they fill up a hot air balloon. So moving around more would hit that thing up. If we lock the volume, so let's lock the volume. Now heating it up, you'll see the pressure go up, and cooling it down, you'll see the pressure go down. And if we have the pressure here at about 5, if we decrease the volume, that's going to make more collisions happen, so the pressure goes up, right? Collisions are going to happen more often if the volume is less. Collisions will happen less often if the volume is more. All right, so I highly recommend you play with this. Here's a way to release some gas if you want to. But play with that to understand those phenomena. And what you should get at the end of that is basically that volume and pressure are indirectly proportional, meaning as one goes up, the other one goes down. And we just saw that if you increase the volume, give the atoms more room to bounce around, the pressure will go down. If you decrease the volume, the pressure will go up. Temperature is directly proportional to volume. If you increase the temperature, the volume will go up. Temperature is directly proportional to pressure. If you increase the temperature, the pressure will go up, and moles is directly proportional to pressure as well. Adding more moles increase the pressure. All right, so pressure of a gas is determined by how many times something collides against the side of the container, basically a pressure gauge, how many times that pressure gauge is getting hit with a gas molecule or atom. Here is a video that I put on. I highly recommend you watch it. I take a balloon and show you some of the effects of atmospheric pressure. I'm not going to get into that right now because that's a 5-minute thing. So basically, when you fill a balloon with air, there's a pressure inside that balloon. And there's also an atmospheric pressure outside the balloon. And those two things are in competition, and where that competition where the front lines of that competition end are where the balloon's edges, right? So wherever this balloon fills up to is the fight between these outside molecules of air and those inside molecules of air. And that's sort of where they've stopped. And what I do in that video is I take away some of these outside ones, and so the balloon can get bigger. So I highly recommend you look at that. The same thing is true with boiling. The reason water isn't boiling right now at room temperature is because there's an atmospheric pressure sort of knocking those water molecules back into the water. And if we took that air pressure away, you wouldn't need to heat up water for it to boil. The water would just leave the liquid phase and go right to the gas phase. I do that as well. And if you think about it, here's sort of a column of air in this red. And at the higher altitudes, there's not as much air because the column doesn't have as many air molecules in it. As you go deeper into the atmosphere toward Earth, there's more and more air above you. And as there's more and more air above you, that means the pressure is increasing. So that is the reason why at sea level you can boil water at 100 degrees Celsius, which is about where we are. If you go up to the mountains, it won't boil at as high a temperature. And the higher up you go, the lower the temperature is because it doesn't have to fight so much atmospheric pressure. If you've looked on directions for cooking in like your macaroni and cheese or some baking things. They'll tell you at higher altitudes to bake it longer, and that's because it doesn't take as much heat to get the water to go away. But if you want the same amount of water to go away, you need to be able to, or basically for mac and cheese, it's just the water's not as hot, and you want it to be 100 degrees. You want to deliver that much energy to the pasta, so it has to go a little longer if it's only going at 90 degrees versus 100. All right, not my most eloquent, but it'll get you through. So in this unit, we got to go back to the Kelvin. We talked about Kelvin and how that at 0 Kelvin, nothing is moving, and so there is no such thing as a negative Kelvin, and that's going to be important. So you need to add that 273 to the degrees Celsius to get the Kelvin. We discussed this already. So 100 degrees Celsius would be 373 Kelvin, right? And minus 23 would be 250 Kelvin, because you just add 273 to that. And the nice thing about Kelvin is it always stays positive until there's no motion. And that's going to be important for this unit. So this unit is going to use some things that make some sense. Pressure symbol is P, volume symbol is V, and temperature symbol is T. As we just discussed, the key unit for temperature will be Kelvin. Occasionally you need to add 273 if I give it to you in Celsius. But temperature for this all to work has to be in Kelvin. Volume has to be in liters. Occasionally it'll be in milliliters, and you can do that now because we did it on every quiz. Now here's the problem. Pressure. Look at this. Nobody can agree on a pressure unit. PSI isn't even listed here, pounds per square inch. These are just 3 of the many ways people measure pressure. And by the way, just review: pressure is collisions, volume is the space something takes up, temperature is related to the movement. So anyway, getting back to pressure, because of these 3 units, this topic is a little bit hard to understand, but you're going to get this. So first of all, if you got to convert milliliters to liters, you just move that decimal 3 places, right? Move it over 3 places, so that's 0.025. Move it over 3 places, so it's 0.4 liters, right? If I give you milliliters, it's always good to put it in liters. That's a standard unit for volume. There are these things called standard temperature and pressure. Standard temperature is, if you had to make one up, you would probably agree 273 Kelvin is a good idea because you're already remembering 273, so you only have to remember one number. And here are the standard pressures for each of the units we'll use. Atmosphere is 1 atmosphere. That's a nice one to remember. Kilopascals, 101, and millimeters of mercury is 760. So just make sure that when you're doing these things that all the pressure units match. There's a combined gas law, and basically this is what you were just learning. If the pressure goes up, then the volume has to go down. That would mean that the pressure times the volume equals a constant. We've done this before. We talked about constants in when we did wavelength. That's what we did, right? As one goes up, the other goes down. So if these 2 equal a constant, then one goes up, the other one goes down. If these 2 equal a constant, then as one goes up, the other one has to go up. Think about it. 2 over 2 equals 1. If I make the pressure 4, that means, and I still want it to equal 1, I need to raise the temperature up to 4. 6 for the pressure, I got to raise the temperature up to 6 so that it keeps equal to 1. So as one goes up, the other goes up. Also, volume over temperature also equals a constant. So basically what they did is they just combined all these things to do this one law, that any pressure, volume, and temperature for a situation of a gas will equal another pressure, volume, and temperature. You're just going to need to put the pressure and volume on top and the temperature in the denominator. And this is for situations like a bubble of some form. Basically, the amount of gas is not changing. So key here is that the amount of gas is not changing. All right, and this is actually why, if you think about it, if you've ever been on an airplane and your chip bag gets really puffy, that's what's happened. Your pressure went down in the airplane, so your volume had to go up. And anyway, all right, moving on. So here's a sample question with that. I give you a pressure, I give you a temperature, I give you a volume, and then I give you another pressure and another temperature, right? So I have P1 V1 over T1 equals P2 V2 over T2. In this situation, all my pressures and volumes are, one second actually, let me change the color of these, or not. I'm going to do that instead, right? So let's do this. All right, so P2 V2 over T2. So basically what we need to do is establish which of these is P1 and which of these is P2. The ones that are associated with each other, this temperature, that pressure, and it's looking for a new volume. Those would be the P2, V2, and T2. And the first ones are the first ones that are in there. So if we look at this, P1 is at 3 atmosphere, V1 is the 318 liters, and T1 is the 293. Those are the three that are related to each other, right? So that's this atmosphere, this temperature, and that liter. And then P2, therefore, would be atmosphere, 2.5 atmosphere. V is what we're looking for, right? It says what is the new volume. Here's the temperature, here's the pressure. So that's your P2, that's your T2. And then you're going to put that into that equation. So we're going to put your pressure 3.0 and your volume 318. And we're going to divide that by your temperature 293. So that's your P1, V1, and T1. And then we're going to make that equal to your pressure, which is 2.5, your volume, which is X, right? Is your X, and your temperature, which is 323. And when you solve for X doing your algebra that we've been going over all year, you get 420 liters. So V2X will equal 420 liters. So basically I did all this math, multiplied both sides by 323, and then divided by 2.5 to get X all by itself. All right, so here's another one. We're going to skip that one real quick. Well, it says STP. So STP means, I guess we're not going to skip this. STP means standard temperature and pressure. And if you remember, that will be given to you that the standard temperature is 273 Kelvin. And the standard pressure is 101, or in this case, since it's looking for torr or millimeters of mercury, that would be 760. So I'll give you those. Don't worry about this. Just worry about setting it up. So you have your volume, your pressure, your temperature in red, and then your P2s, V2s are right here. Here's your pressure, here's your volume. It's looking for the new temperature. That's your T2. So when you set this up into that equation, it's going to be 760, your P1, 895, your V1, divided by 273, your T1, and that's going to equal your P2, which is 1277, your V2, which is 574, and then your T2, which is your X, basically. So you're going to do that math, and you're going to get a temperature equal to, let's do this real quick, I guess, because I didn't have it all done. So 760 times 895 divided by 273 is 2,491. So this is, let's keep it in the color, 2,491 is equal to 1277 times 574 is 732,998 divided by T2. So what you need to do is multiply both sides by T2 and then divide 732,998 by 2491. So 732,998 divided by 2491 is going to equal your T2. Divided by 2491. It's 294. So your T2 is 294 Kelvin. All these have to be in Kelvin. All right. So here, when you see temperatures that are not in Kelvin, that should be an indication that you have to get them in Kelvin. So 65 plus 273 is, hold on a second, 74, right? 348. We need to back that up, but I'm pretty sure that's right. 65 plus 273 is 338. Oops, 338. All right, so 338 for that one. 338 for that one. And for the other one, 45 degrees, so you're going to add 273, and you're going to get 8 and 11 and 318 Kelvin for that one. So now we're setting this up, P1V1 over T1 equals P2V2 over T2. Now notice something's held constant here. The volume is held constant. So that means that V2 is equal to V1. And because of that, they would eliminate each other from this equation. If that doesn't make sense to you, you can just set them both equal to 1. Since they equal a constant, you can just set them both equal to 1, and it'll make your life easy. So then we got our pressure is 0.25. Our V, we just said, is 1 because they were constant. Our temperature, we figured out to be 338. And that's going to equal the new pressure, which is what we're looking for, P2. Our new volume is the same as our, right? It's the same as constant, so it's 1. So V2 equals V1 equals 1. And then you divide that by the 318. And you're solving for P2. So in this case, you just do 0.25 times 1 divided by 338. And we get 0.0030. Second. 0.30739. Thanks for nothing. 739. And then that's going to equal P2 divided by 318. So then we got to get that 318 out. So we multiply both sides by 318. And you get your P2 equals 0.235. So P2 equals 0.235 atmosphere. All right, so let's clear all that and see how I did that. 0.235, right? So your pressures, your temperature. Oh, should have just done it that way. Would have been easier. All right. Here's your P1 and your T1. Since V2 and V1 are the same, that's a constant. That means you can just drop them out, or you can set them both equal to 1. So if you move on to another class, they may tell you to memorize these laws: Boyles Law, Charles Law, Guy-Lussac's Law. Basically, they're the relationships we already just talked about. That if pressure goes up, volume has to go down. So P1V1 equals P2V2. That would mean temperature is constant, so it's removed, or it equals 1. If pressure is constant, then it's equal to 1, or you take it out. So you just get V1 over T1 equals V2 over T2. So here I talked about if temperature is constant, so the T1 and T2 disappear because it's the same thing. You can make them both equal to 1. And if volume is constant, it's P1 over T1 equals P2 over T2. So hopefully you see how all of these are some derivative of what we've been talking about. P1V1 over T1 equals P2V2 over T2. Right? And whichever one is constant, you just drop out. If temperature is constant, then you drop out the temperature. If pressure is constant, you drop off the pressure. And if volume is constant, you drop out the volume. So rather than memorize all these equations, it's just nice to memorize one equation. And if the question doesn't talk about one of the variables, then you just don't deal with it. All right, so now we're going to talk about ideal gases. Ideal gases, if this I asked you what your ideal meal was, some kids sent me some of this stuff as their ideal meals and their ideal pets. We're going to talk about ideal gases. And an ideal gas, this is what you might want to ask for a picture of an ideal gas. An ideal gas makes certain assumptions about the gas. That is that the particles of the gas are small, hard, with a negligible volume. So that's not too hard to figure out if you think about what we were just doing here. I left it open, I hope. Good. Right? Small, hard, bouncing around. That's not too much to ask. Motion is rapid, constant, and random. Would you say here that we have rapid, constant, and random motion, right? There's no telling where these things are going. They kind of just bounce all over the place. And then the other assumption is that the collisions between the particles are perfectly elastic. They're like billiard balls. No energy is lost. Now that actually falls apart a little bit in a real gas. What it's saying is these gas particles won't be attracted to each other in any way. And that's not entirely true, we know, because we learned about intermolecular forces and London dispersion and all that. So there is a slight attraction between these atoms or molecules. And because of that, that's where this falls apart a little. But it's pretty much true. So we use it because look at the nice little equation you get when you use this. You get this nice equation, PV equals nRT. So that's called the ideal gas law. It's the pressure times the volume equals nRT. Now, if you think about that, if you divide both sides by T, you get PV over T equals nR. N is moles. Thank you, computer. N is moles. And R is what we call a gas constant. So think about it. If you don't change the number of moles, if you have a balloon or a bubble or some certain amount of moles, then PV over T would always equal the same thing. It's always going to equal the same number. And if we were able to hand it out together, we would do a lab of that. Unfortunately, we do not. So anyway, there you have it. So PV equals nRT. This is a nice little equation to use. Basically, I will have to give you the R. Now notice there are 3 R's, and what distinguishes each R from the other is that we have these stupid 3 units of pressure, and so therefore all 3 units of pressure have to be represented in the R, and each R therefore has a different number. So you have to just make sure whichever R you use is the R that you need for that question. So let's take a look here. I have 1 mole of gas at 273 Kelvin, still everything needs to be in Kelvin, and 1 atmosphere. So which of these R's do I need to use for this problem? We're going to use this equation PV equals nRT. Here's our temperature, here's our pressure, here's our moles, which is N, thank you science. We're looking for our volume. So the only thing we need to know is which R to use, right? We got a P, we got a V, we got an N, we got a T. We just got to figure out which R. And the units of the pressure dictate which R you use. So in this case, we're going to use that first one as our R because 0.0821 has atmospheres in it, and we have to make sure everything matches. Again, this is just giving you the idea that sometimes when you go to a vending machine and you only have dollars and it only takes coins, it's not going to work. Well, that's the way this equation works. It only works if you match the units, and the units have to be atmosphere for your R because your units of pressure are an R. So then we just plug all this in. So 1 atmosphere times the volume, which is what we're looking for, equals the N, which is 1 as well. The R we just chose is 0.0821, and your T is 273. So if you do that, you get 22.4, which is the number of liters any gas will occupy at standard temperature and pressure. So that's a nice little thing to know, that 22.4 liters is how much 1 mole of gas. Doesn't matter, right? I didn't say what kind of gas this was. It could be water, could be hydrogen, could be ammonia, could be chlorine. They all would do this if you had 1 mole. All right, let's go into this some more. So child's lungs can hold 2.2 liters. How many grams of oxygen do her lungs hold at a pressure of 762 millimeters of mercury and a body temperature of 37 degrees Celsius? So the first thing, hopefully you realize, you got your pressure, you got your volume, your temperature has to be in Kelvin, right? For these to work, they have to be in Kelvin. Celsius can get negative, and we don't want this to get negative because then we'd start getting negative space. And what does negative space mean? And then we have this N is what we're looking for. So which of these R's are we going to use? Remember, we look at our pressure units. So we're going to use that R right there. And we set that up as 762 times 2.2, which is our volume, equals the N is what we're looking for. Our R is 62.4, and our T is 310. Okay, so then you just do that math, and you get 762 times 2.2 is 1676. So So 1676 equals 62.4 times 310 equals 19,344 times n. And so to separate your n, we want to divide both sides by 19,344. And you get 1676 divided by 19344 is 0.086. So the answer is 0.086 moles. All right. So in this one, we have 35 grams of carbon dioxide. All right. And we have atmospheres and we have milliliters. So we got to first, we know we got to move that milliliters to liters, right? Move that over 3 places. Atmospheres is fine. Grams is no good. So grams have to go to moles. So if we're going to turn 35 grams of carbon dioxide to moles, we got to use that periodic table and turn grams into moles. So carbon is 12, and oxygen is 16, and there's 2 of them. So that's 32, and 12 is 44. So that's 44 grams in 1 mole. So 35 divided by 44 is 0.795. So our moles is 0.795. It gave us grams. We had to convert to moles. So which R do we want to use for this problem? We're looking at our pressure, which is right here. So atmosphere one, we want to use as R. So pressure 0.25, volume 1.55, because we did that, that's our volume, equals N, we figured out our N, 0.795. Our R, we just figured out is the 0.0821. And the T is what we're looking for. So T is the unknown. Can I do this one? All right, so there's the math that I did. I'm showing you there if you look at this without the video, and then the answer or no, what do you think? I don't. So 0.25 times 1.55 divided by 0.795 divided by 0.0821. 5.93 is our temperature. It's 5.93. That's pretty low. Is that really what happened? 0.25 times 1.55 divided by 0.795 divided by 0.0821. 5.93 Kelvin. There you go. All right. It's pretty cold. So basically, the point of this quiz will be when to use one of these and when to use the other one. I'm posting homework so you can practice both of these, and I will also post another video that really boils down and walks you through some more problems. But basically, if you're ready to go for this, it tells you if you have multiple pressures, multiple volumes, multiple temperatures, that's where this equation works. Remember, everything has to be in Kelvin, right? Kelvin is true for both temperatures for both of these. And also volume in liters isn't a bad idea for this one and is a necessity for this one. So if you're given more than one pressure, you want to use P1 V1 over T1. If you're given only one of each and you're given anything like moles or grams, that's a big hint that you have an N in this equation. If you do not have moles or grams, that's a good hint. You're going to use the P1 V1 over T1. All right, so there's plenty of homework to try out. That's all I'm going to do right now for this because it's already too long. And please Zoom me if you have any questions.